So, actually, there's an easier way to explain what we're doing today. Criteria. So a year ago, I was like, I can probably take a 4-year engineering degree in 2 classes, right? Why would I not be able to do that? So I looked up the things you have to learn in a 4-year engineering degree, and I just thought I would teach them all this term. So this is what we're doing. We're doing algorithms, complexity, computer science theory, concepts of programming languages and software development, general purpose language, architecture, organization, information management, all this stuff, right? But what are we missing? We don't have discrete mathematics, so I have to teach you graph theory, okay? All right, lock in. Okay, so welcome to Systems in Rust. How's everyone doing today? Did y'all like the LA Times crossword? If you were a little more locked in, we could have finished it in those 3 minutes, right? So let this be a lesson that the locked in level needs to increase, okay? I'm guessing traits is not the monumental time sink some of the historical assignments have been in this class. So I'm guessing you're probably doing okay with that. I felt some obligation to teach you traits because you've probably been using methods your entire life. Today I'm going to teach you graph theory. Specifically, I'm going to teach you graph theory in the following ways. I'm going to teach you what graphs are. I'm going to teach you what DAGs are. Then I'm going to teach you what trees are. Then next week, we're going to learn a tree optimization. And then we're going to be ready to do the version control system stuff. Okay? What are graphs? A tree is a type of graph, which is why we're learning graphs. And a graph is a pair. And by that I mean like by definition. Like if it is not a pair, it is not a graph. If it is a graph, it is a pair. I got monumentally confused the first time someone started talking about graph theory in one of my CS classes. So I'm going to draw something on the board that is not what I mean by graph. Am I going to do that? No, psych. Okay, I can't find the markers. Oh, no, I can find them. Here we go. I do not mean one of these critters, okay? This is fine. Perhaps we would instead call this, now, for the sake of this class, a graphic. This is not what I mean when I say graph. Do not visualize this in your mind. It is a mathematical object, okay? Now, this can be a representation of a graph. That's fine. So, a graph is a pair of a set of nodes, or vertices, or vertexes, and it is a set of edges. What are the edges? They are pairs of nodes. The edges may or may not be ordered pairs. The graph has to be an ordered pair. I find graph theory a lot easier to get my head around than some of the other branches of mathematics we've looked at this term. I think field theory, ring theory, those things are absolutely brutal. Graphs seem quite straightforward to me, so I hope they seem straightforward to you too when I'm done talking about them. I'm going to introduce graphs using a running example, and this running example is going to try and distract you from the stock market graph that I put on the board. And so famously, it's about the trains running on time. So I'm going to use the example of Amtrak. You can call this a running example, a training example, a running train, or a training run. All of those are acceptable. Okay. This is Amtrak. This is a visualization of Amtrak. This is a visualization of Amtrak actually in 3 space projected onto the surface of a globe. You may note that this is an animation. This is one of our first animated slides this term. So if anyone asks if there is innovative and something pedagogy in this class, that is a big yes. So if anyone asks. You might even want to suggest that the course materials were continuously improving across the course of the term. If someone asks you that, that would be another thing you could say. And if you don't feel like that, that's fine. Then you should probably keep your mouth shut, right? Like you don't have anything nice to say. Okay, so graph is an ordered pair. That is 2 things in a fixed order. It can be thought of as a sequence of length 2. If you are extremely into Python, you're probably thinking of it as a list of length 2. What is the problem with Python? The problem with Python is it is not formal mathematics. And it cheats a little bit because it has built-in lists, so we're going to build our own thing. I want to point out something that a graph is not. A graph is not a set. A graph is a pair of sets. But a pair is not a set of size 2 because a pair is in order. So we have a pair of sets, that is the type. If you're familiar with type hits, you can imagine type hints, goodness sakes. You can imagine how we would write out, oh, this is a pair of sets. Why is a graph not a set? Because in a graph the pair is in order, and in a set the elements are not in order. I think this is a link to 303. Is that true? Yeah, that's Katy Perry in 303. Okay, cool. You can watch that after class. You don't have to. Wow, I'm so distracted. Why did I do that? Wow, we're so far. Okay, so what do I mean by a pair? I mean the ordered pair. I think of ordered pairs in terms of points in 2-space in a coordinate grid. I know this is going to become increasingly confusing with the graph example. So we can imagine that we have a number plane and we are trying to specify a location in this plane. How are we going to do that? We are going to do that with an ordered pair. We're going to look at the ordered pair 0.5, 1.5, and we're going to put it in red. Why does the ordering matter? The ordering matters because over here, this point where I have my cursor is also 1.5 from one of the axes and 0.5 from another axis. But it is in a fundamentally different location. So ordered pairs can matter in a lot of examples, and they matter in this example. In this case, I'm denoting it as being ordered using parens. So what am I going to do? I'm going to assume the existence of sets. Is that okay? Can I assume the existence of sets? Okay. I can rigorously define sets, but only if you make me. Actually, I don't know how to rigorously define sets. It's a collection of things. It's an unordered collection. But I am going to make ordered pairs out of sets. So we are going to say an ordered pair is a set of cardinality 2. And I know what you're thinking. You're thinking, you just said a pair isn't a set with 2 elements. Okay. It is a little bit a set with 2 elements, but the 2 elements are weird as heck, okay? They're not what you think they're going to be. Or maybe they are. Maybe you've been working at it. One element of the ordered pair, of the set representing the ordered pairs. So I'm going to take 2 elements, and one of the elements I'm going to put in it is it's going to be a set, and that set is going to have cardinality 1. I'll draw this on the board. I'm going to grab a marker. I've been extremely into markers today. I forgot how to do matrix multiplication last class and had to Google it in front of the students. That was kind of silly. Okay. So if I want to represent AB as a set, I can't just put it in a set like this because I lose the notion of order. So what am I going to do? I'm going to create a set of 2 elements. I'm going to put a comma in the middle. And the first of the 2, or one element of the set, it's not the first, one element of the set is a set of cardinality 1. So there's going to be another set in here that only has one thing in it. The other element of the set is a set of cardinality 2. So this is going to have a comma. The element of the set of cardinality 1 is one of the 2 elements of the set of cardinality 2. I'm going to call that element A. And it's going to go in both places. Okay? And then there's one other element here which will denote B. Okay. This is an ordered pair. Why is this an ordered pair? Because using only unordered sets, I'm able to determine which of A and B comes first. The element of the pair, which is an element of the set of cardinality 1, is the element we can regard as the first element of the ordered pair. Is this like the craziest thing you've ever seen or what? Did you notice that I made an ordered collection out of unordered collections? You're all taking this quite well. This blew my mind. Okay, that's fine. Maybe you'll be grinding out something later and you'll realize how cool this is. Anyways, I lost a lot of sleep over this one when I saw it for the first time. Okay. The element of both sets is regarded as the first element. I'm connecting these two conceptually. We can't do this in Python. Why can't we do this in Python? I'm going to show you one reason that Python's the worst. I have ranted at Python at various points in time, both to you and not to you. So I'm going to make an A and a B. Can I do it this way? Do you ever think about how many characters we have to type in a given day? Okay, so that's no problem, right? We understand what's going on there. Can I put A inside a set? Of course I can. Can I put A and B inside a set? Of course I can, no problem. Then I'll simply make a set that contains the set A and a set that contains the set B, A and B. And you're not allowed to do that in Python. What is happening with my screen? Because you can't put sets inside of other sets in Python, which means Python integers aren't integers, Python floats aren't reals, Python sets aren't sets. Just learn Rust, right? Tell all your friends to learn Rust. Tell your enemies too. Maybe tell your enemies first. Okay. Why do I point this out? We should not rely on implementation details in Python to determine the correctness or incorrectness of formal mathematics. You are allowed to put anything inside a set you want, including another set. I've put sets inside sets. I'm doing that here. So when I say ordered pair, this is what I mean. An ordered pair, AB, is equivalent to the set that contains the set containing A and the set that contains A and B. It's this thing. So this is my formal definition of ordered pair. Why did I define this rigorously? Because now I'm allowed to use ordered pairs, which are going to be real useful coming up. Okay. So we're going to introduce something here. I call this the sort of head operator. I don't know what else to call it. But what is the head operator? Well, we can determine the head element of an ordered pair by looking in our set of sets and taking the intersection over the set of sets. If we take the intersection over A and AB, what do we get back? Only A is present in both of them, which means this equals A, which means the head of the ordered pair is A. So we are able to extract order back. I have expressed this in two ways. I have done this with big intersection, showing the intersection over all of the elements of the pair. And then I've also said for all sets that are element of the pair, X is an element of the set. Do you have a preferred one of these notations from any of your background? Okay. I don't know how much math you all have before you get here. Is this a lot of math or a little bit of math? Out of 10, how much math is this? It's 5 out of 10. 3. Oh, I got like a 7 or something. Okay. No one said 0 or 10, which means we're fine, right? Okay. Thought I'd go ahead and hit you with the quick set minus, right? We got the set minus in here. Do you notice that I asked you how much math this was before I used a set minus? Okay, so we can also denote tail. What is tail? Well, we take all of the elements that are in both sets, which is A and B, and then what do? We subtract all of the elements in the intersection. So we subtract A, and that gives us back B. So B is the tail of the ordered pair. This one is a little more annoying to write out, but not that bad. So, when I'm talking about an ordered pair, G, which refers to a graph, my haters and my doubters would say, I don't know that you can make that with just sets because sets aren't ordered. But I totally can, and I did. This is an ordered pair made out of sets. A graph, which is equal to a set of vertices and a set of edges, can be thought of as a set of vertices and a set of vertices and a set of edges. So I can make the whole thing out of sets, which means I've secretly been teaching you set theory this whole time, not graph theory. So make sure if anyone asks if you ever had a set theory class, that is a yes. Okay? All right, you got that? Okay. Cool. You know number theory, you know set theory, you know field theory. Covered anything else? You know Rust? Okay. V is one of the two sets in our ordered pair. It is usually thought of as the first set in the ordered pair. We usually use V for this because it is referring to vertices. What do I mean by vertices? Well, if I represent a set of perhaps 4 dots that have edges connecting them, big polygon would have you believe that these corners here are something that can be referred to as vertexes or vertices. We can also think of them as nodes. Why do we think of them as nodes? I don't know. I have no idea what a node is, so I've just called them nodes forever. In the case of the Amtrak example, the nodes are going to be stations or stops or cities. I can give you one example. On days that I can get away with it, I take the Amtrak bus from Portland Union Station to the thing across the street over there. I'm guessing it's called Salem Union Station. I don't know. It also stops in like Wilsonville, Woodbridge, Would you ever believe that it stops somewhere else? And it also stops in either Tigard or Tualatin, and I don't know which one, and I also don't know the difference. Okay? So, in a north-south, you have Portland, you have either Tigard or Tualatin. I'm writing Tigard because it's shorter. Is Wilsonville north of the Wood Place or not? It's north of the Wood Place. Wilsonville. You're seriously just going to keep making me say the Wood Place and not tell me what it is?
It's Woodburg, I think.
Woodburg, got it. Okay. And then there's salami. Okay. I sometimes refer to my cat as Salami, which she loves. She likes pretending to be a piece of salami. She doesn't seem to like salami itself, but she likes pretending to be salami. So, these are the nodes on the graph. Okay? What are the edges? The edges are the connections. Now, I'm going to make a simplifying assumption. It is in fact true. You can take Amtrak from Portland all the way to Salami. I'm not going to regard that as an edge. I'm going to think of today only what I'm going to call the atomic edges, which is edges with no stops. So I view there as being an edge from Portland to Tigard and from Tigard to Wilsonville, but I do not view there being an edge from Portland to Wilsonville. Why am I doing that? Because it's easier. That's all. You can think of it that way. That's totally fine. Doesn't matter. On Amtrak Cascades, which is the train, the immediate stops north and south of Portland are Oregon City and Vancouver, WA. Can you believe how many Vancouvers we have? There's at least 2 Salems, 2 Portlands, and 2 Vancouvers, right? But there's only 1 Woodburg, right? So, an Amtrak is an ordered pair. The 2 elements of the pair are stations and train connections. So, Amtrak is the ordered pair of stations and trains, is how I'm going to call this. Okay. My favorite Amtrak train that connects Eugene to Vancouver, got to be specific to make sure you're not playing favorites, is the Amtrak Cascades. Fun fact about the Amtrak Cascades, I am 100% sure it is unconstitutional for the following reason. It is operated by the Departments of Transportation of Oregon, Washington, and British Columbia. And not one of those 3 organizations is allowed to make an agreement that crosses international borders, according to the constitutions of Canada and the United States. So, for some reason, the state of Washington is negotiating, I don't know, like it's an enumerated power to the federal government in the Constitution. I don't know if you've read the Constitution recently. I would not recommend it. It's like 7 pages long and none of it makes sense. But it is definitely against the law for Amtrak Cascades to exist. So I love taking it because I'm a criminal, right? Wait, no, I think in this class we decided I'm not a criminal. I don't remember which story we were going with. It is always hard to keep track of which version of the truth I have told where. Okay, so the Amtrak Cascades, which exists in open defiance of the United States Constitution, not unlike myself, has these following stops. Some of you may have heard of some of these. So there's Albany, that's where Professor Kitato Smalley is from. There's Olympia, which is the state capital of Washington. There's Seattle, which is where the worst coffee shop ever invented is from, Starbucks, right? There's a few other things on there. There's 2 Vancouvers for some reason, and then there's Eugene, which is where people that win the U.S. Track and Field National Championship are from, right? So we've got a lot of things on here. And then there's some places that don't really exist, like Centralia. Never heard of it, right? Anyone ever heard of Centralia? That's right. Put your hands down. Okay. So I did that last year, and someone was from Centralia in the class, right? So it's actually good to do a bit of research before you throw things out like that. So anyways, these are places you can go on Amtrak Cascades. And an astute observer may note, wait a minute, those aren't in order. Correct. They are not in north-south order. They are in alphabetical order because I had to put them in some order. I did not put these in order geographically because they are elements of a set, and they are not supposed to seem in order to you. Okay. Now, let's restrict ourselves to the parts of the Amtrak Cascades route that matters, right? Because as we know, if you've ever been to Oregon, there's basically nothing in the entire state south of Portland, right? It's just it's Portland and then it's dust, right? So I've personally never been south of Oregon or south of Portland in Oregon, so I have no idea what's there. So I assume that the Pacific Northwest begins at the southern terminus of Portland and continues north to the northern terminus of Seattle. And if I were to do that, then I would get to ride the train 6 times a day instead of the only 2 times a day you can go to Salem. And I would only go through these, I think, 8 stops, right? Centralia, which doesn't exist, Kelso, Olympia, Portland, Seattle, Tacoma, Tukwila, and Vancouver-Wa. So we've eliminated the unconstitutionality doing this, by the way, as well, right? So we are now no longer violating Article 2, might be Article 1, of the Constitution. So what are our edges? As you know, both Salem, no, sorry, dang it. It's hard to make fun of so many cities. Both Seattle and Portland pride themselves in having an edgy youth culture, right? So I believe Nirvana is from Seattle, and I believe Having Bad Opinions is from Portland. So we've got a lot of edginess coming from all of these places. I went to a great local emo concert the other day. It sounded so bad, and that's exactly what it should sound like, right? So E is a set of elements, and we term them edges, links, lines, connections. The edges are pairs of vertices, and I know what you're thinking. You're thinking, oh no, not pairs again. I sure hope they're not ordered pairs, and I don't have to listen to an entire lecture about making ordered collection out of unordered collections. Not to worry, that only happens at probability 0.5, because you get to decide whether your graph is a directed graph or an undirected graph. 2 of the best kinds of graphs, right? And so, let's give an example of a directed graph. Imagine I am one specific train. For example, the Cascades, I think 704 is the one that I usually take. Trains that exist in Amtrak can only go in one direction because they are objects of the class train. They are initialized at a certain train station. They progress to another train station, and then their deconstructor is called, and they cease to exist. And the way they cease to exist is just the number that is listed on the train changes. But in terms of formally how it exists, the train stops existing. So trains can only progress north to south or south to north. So what that means is, from the perspective of one train, I can have a connection from Portland to Tigard, but that same train cannot have a separate connection from Tigard back to Portland. This is not possible. This is not allowed. That is a directed graph. Now, what is an undirected graph? Well, Amtrak is an undirected graph because there are no stations for which Amtrak does not serve in both directions. So even though there is only one train that goes one way, because Amtrak is a collection of trains and therefore a collection of edges, it has edges going in both directions. So to Amtrak, Portland Tigard is not ordered, but to the Amtrak Cascade 704, Portland to Tigard is ordered and is present, and Tigard to Portland is ordered and not present. Here is an example that you might care about a lot of an ordered graph. It is the graph that you implemented for stack. The nodes are the stack structs. The edges are the box misdirect pointers. and those boxes only go in one direction. You can dereference them to go back, but you may have noticed if you go to the end of your stack, or especially the end of your queue, there's no real way to get back to the middle. So, many of the data structures that we implement in computers, especially when they are heap allocated, when you're using box, are directed graphs. Another thing that is directed is the internet. If I type something into the internet, I can go to that location. If I open my terminal, I can curl xkcd.com. How do I do this? Let's see. Oh, I probably have to say like H. Does anyone know how curl works? So it's fairly easy to yoink things off the internet. Look, it's best viewed with Netscape Navigator 4.0 or below on a Pentium 3 plus or minus 1 emulated in JavaScript. Okay, I'm going to stop reading that. That's clearly nerd sniping. And so it is relatively easy to yoink things off the internet. I have often been referred to as the yoinkster for my regular engagement in yoinking. It is relatively difficult to put things onto the internet. And for example, there's no just like isolated command I say. I can't say like lurk hello there, https://xkcd.com. And I cannot just post something to the internet by saying curl backwards, right? It requires setting up a server. Sometimes I have to pay someone money, either someone that is hosting the server or the power company. It's emotionally exhausting. And so as a rule, we do not engage in web development unless we need one upper division elective to complete our CS major, in which case we enroll in CS 262 offered next semester. Now, depending on your catalog year, it might list every possible course other than CS 262 because for some reason they list 261, which isn't offered anymore, 263, which isn't offered anymore, and 276, which was already offered this term. So your SAGE might look like a hornet's nest, okay? If that is happening to you, sign up for CS 262 and send me an email, and I'll get it sorted out for you. Okay. Does anyone need any help with advising? Okay, email. Okay. The advising system is a directed edge coming out of the registrar's office and passing through us. And that's great. Okay, so remember how I said these sets weren't ordered? Unfortunately, I am but a mere mortal. I am not a set theorist. And so I had to put these in order to understand them. Centralia and Kelso Longview is an edge. Seattle and Tacoma are not edges, because they're too far apart. Okay, so our edges are pairs of adjacent stations. Oh! That's a rendering error. I don't know what I was trying to do. I'm guessing I was trying to italicize adjacent. But do you all know? Sorry. Okay, this is super relevant. Let's see. Dillinger, first try. So you know how you can do this in Markdown? Okay, so you can use dashes to do bullet points in Markdown. I hate that. Or no, I like that. Okay, sorry. No, I love this. You can also do asterisk, which I don't like. But, can I do this? If you ask computer, make a Markdown list of reasons set theory is based. Why is it so slow? Okay, no, render as a copy paste code block. First try. There you go. Okay, so look, okay. Now, far be it from me to claim that Google Gemini is super intelligent and capable of artificial general intelligence and worth a valuation of $4 trillion. But it uses asterisks for its bullets, right? So, what do? Right? It likes emojis too. I said, well, okay, I'm going to replace. Can I do this? Oh, I don't know how to find a replace in here. Anyways, Obviously, I didn't write this myself. I used ChatGPT to generate it, right? But it made all of my bullet points with asterisks instead of dashes, which I hated. So what I did is I manually replaced all of the asterisks that were followed by a space with a dash. But this was an asterisk followed by a space that was meant to be an italicizing asterisk. So there's just an asterisk here and there's a minus here. I thought that might be interesting. Learn about this and more in CS262 Web Development, offered next term. Okay, so there are 8 stations, so there are 7 edges. Why is that? Fence post problem, we're off by 1, right? So we lose 1 cardinality to our set when we go down. I'm just thinking of these as unordered at this time, but it doesn't matter. I use tuple notation here with parens. Doesn't really matter what you use. Okay, so we can express G, the graph G. What is G? We can express G only using sets. I think I turned these into arrays because I don't know how JSON works. I don't think it actually matters. But we can express G, the graph of the Amtrak cascades connecting Seattle and Portland and vice versa, only using sets. And the way we do this is we have a set of vertices and we have a set of edges. And if you want to, you can make this all sets by doing the double nesting set thing. So now it is time for an exercise, not just because I've been yelling and my voice hurts. I always forget that I don't actually have to yell because it seems like I do. I think I can talk like this and you can still hear me okay, right? But then I don't get to properly express my enthusiasm, right? Ooh, set theory. Okay, Amtrak recently added lines. This is a little bit older now. I think it's like 3 or 4 years now. But they fortunately recently added a line that only has 4 or 5 stops on it, which is extremely convenient for my use case. This is called the Hiawatha, which is named after the real or actual chief of the Longhouse people who are called the Iroquois and refer to themselves another way. I forgot we're doing land acknowledgements today. This is not the name of the people. Can I say that? Haudenosaunee. The Haudenosaunee are really cool because if you go to their website and read their origin story, it actually goes back before recorded history, which is extremely rad. I haven't seen that very often. This website is very cool. You can check them out. But the About Us is real cool. Anyways, I was first told about Hiawatha by, of course, my ancestors who were colonizers, right? And they referred to Hiawatha as a chieftain of the Iroquois, not the Haudenosaunee. But this train line connects Milwaukee, and not the Milwaukee in South Portland, right? The Milwaukee in Wisconsin, right? So there is a lot of cheddar cheese in this Milwaukee, right? But there is not a lot of scene kids, right? There might be scene kids in Milwaukee, I don't know. And the world's greatest city, Chicago, Bears, Cubs, Sox, Bulls, right? We all understand that. Okay. I just want to, I would like you to share in my love of Amtrak, so I'm going to read this description to you and just think about how cool Amtrak is. From the grandeur of Grand Parks, Buckingham Fountain, to iconic museums and skyscrapers, see for yourself why Chicago was once dubbed Paris on the Prairie. Engage in retail therapy on the Magnificent Mile, or root for the home team within the friendly confines of famed Wrigley Field. Okay, so your job is to go to this link, look up the Hiawatha route, which is right here, and make a graph of it in JSON. You can test if your JSON is accurate on the web, or you can do this. You can install JQ, and it will check. Ready, go. I have to go to drink something. You can work with your neighbor. You can also vibe. So I'm currently working on my own graph, which is a directed graph between the clues and the answers, right? And you can only go in one direction.
36 crosses stupid Cupid.
That's so fun. Okay. Okay. What's that make this? Forming couples? Okay. I wanted to check something. Cascade.json. Do I have JQ? Okay, cool. JQ Cascade. What? Did I not save it? JQ Cascade.json. Cascade is not defined. What am I doing wrong? Oh, okay. Huh, I thought that'd work. What's wrong with this? So I thought I could change these to be unordered. And that wouldn't change the correctness. I don't know if that's true or not. I don't know. Okay. I don't actually know anything about JSON, and I don't know if I'm supposed to. I think it was like a pretty big deal a while ago, and now everyone's using the arrow formats, which are Feather and Parquet. But I don't know if that's absolutely correct. Does anyone do web dev at all? Do you use JSON?
For what exactly?
Anything. Like data storage or?
Yeah. JSON
Okay, it's still used a lot. Plain text format. Okay. So learn JSON. Yes. Yeah. It's helpful that it's both JavaScript and Python, or very, very close to it. So that's kind of cool. A DAG is a directed acyclic graph. Okay, my voice is going to perish. Okay. On the screen, I have a DAG. The directionality is represented by arrows, otherwise unsurprising. It is acyclic. You can think about what you probably think that means. I'm going to find it here. Okay. We have more gore. Look at this. We lost. And this isn't correct anyways, because these shouldn't have been italicized. These should be LaTeX script. Man, I looked at this yesterday and it looked fine to me. Okay. I ran out of brain yesterday from advising. It was really bad. So if I sent you an email that's like, you should take 7 classes next term, ignore that. I'll follow up. I'll tell you something that makes more sense. And you probably should not listen to me anyways. Okay. We can think of edges in graph as, what else? A homogeneous binary relation. Okay, you should know what these words mean, so that's why we're teaching them. There is a great deal of information I'm teaching you today that I could have obscured from you. Like, obviously, I didn't have to teach you how to implement ordered pairs with sets, right? Why am I teaching you this stuff? Why would I not, right? Like, it's valuable to know how to construct one data structure out of other data structures. That's just like a useful thing that you like might have to do sometime when you're trying to solve a problem, right? At least my experience was, and I think I might have to reevaluate this in a few years because it seems like I'm not on Stack Overflow ever anymore, and I felt like I was living on there for a while. A lot of people on Stack Overflow use the technical mathematical terms to describe things, right? Like that was just, and why do you do that? Well, it's the only unambiguous way to describe them, right? So if someone asks like, hey, what are the edges in a graph? Well, it's a homogeneous binary relation. Like, we shouldn't call it something other than what it is. So what does homogeneous mean? It means from a set to itself. What do I mean by a set to itself? So it means it goes from Portland, Salem to Portland, Salem. What is an example of a homogeneous relationship over, for example, the natural numbers, addition. When I add two natural numbers together, I get a natural number back. What is an example of something that is not a homogeneous relation? Subtraction. 3 minus 5 is not a natural number. So addition over the natural numbers is homogeneous, subtraction is not. What does binary mean? It means over two elements. Addition is not a great example here because I think it's pretty easy to say, what is the sum of 3, 4, 5? And you would say 10, presumably. I don't know. Right? But sometimes you can only take two things, right? And so a train can only connect two stops without touching one other stop. So an atomic connection on a train is necessarily binary. What is a relation? You thought I wasn't going to use set theory for anything else. A relation is a set of pairs. So you've seen this notion of edges. Well, a set of pairs is just how we relate things to each other. So what we can say, you can express addition quite simply. This is 1. That looks like a 2, doesn't it? I'm going to try again. 1, 1 is in a pair with 2. This is an ordered pair of an ordered pair. This is in a set. And we can say plus is the set of all ordered pairs of additions over the natural numbers, right? We're not restricted to having a finite number of things inside our sets, so this is completely reasonable. So, why are we defining this? We're defining this because we're trying to get to the point where we can define cycles. And I'm going to do that by I'm going to take, I'm sorry, this is a lot of words. I know it's a lot of words. It's 5 technical terms in a row. The transitive closure over a homogeneous binary relation. Okay. I suspect if I said that to a middle schooler, they would instantly fall asleep and never wake up again until they became a math major in their 20s, right? Which happens to a lot of us, right? I'm saying it to you for the reasons I introduced. So I'm going to take a transitive closure over edges. How am I going to do that? Well, I'm going to take the Cartesian product. You thought I wasn't going to introduce another technical term. The Cartesian product. Okay, a relation R over a set S is a set of pairs of elements of S. What is S? Okay, so because it's Cartesian product over S, S is the stations. The set of pairs of elements are the connections between stations. But in this case, when I take the Cartesian product over the set of stations, it's every pair of stations. Portland, Salem, Portland, Vancouver, Portland, Narnia, whatever, right? So a relation is a subset of this. So I'm going to take a subset of the set of all pairs of elements, and that is going to be a relation. So, for example, 1, 1, 2 is a subset of all of the possible pairs of a pair of natural numbers and a solution, right? There is not 1, 1, 3. So I'm going to use big X for this, big times. And I'm accustomed to seeing this. I'm going to show you 2 ways. I'm going to try and use it on the slides. As with like this thing, where my typesetting doesn't work correctly, when I am teaching this type of content on slides with embedded whatever, I'm sort of at the absolute limits of my typesetting ability to be able to write something down that is clear. One of the reasons I'm at the absolute limit of my typesetting ability is I wasn't formally taught any of this stuff when I was learning it. So I'm showing you how I render it. If I were to say S times X, the Cartesian product in LaTeX, I would get so this is like math BBS, right? That is just backslash times in LaTeX. Will this work? Do I have to zoom out? Render. So that is the same thing I'm showing you on the slides. This is a much lower resolution image, right? My slides are using vector graphics, so they're infinite precision. You don't have to use LaTeX to describe this. I was really on a kick for a few years where I was trying very, very hard to represent all of my mathematical formulae in HTML. I came across some things that I just couldn't do gracefully without using divs and a lot of web dev. But if you want to do that, no problem. We can italicize the S. We can do a Unicode times character, which is this one. And then we can do another italicized S. So both of these things work. And in fact, if I save this, let's copy that. Cart. Nope, that's not what I want to do. Why is it? Did I not copy this? I thought I did. And so that's the same way of representing this in HTML. Okay, so we're going to use, for a motivating example here, the set of traffic light colors, green, yellow, red. Why am I doing this? This is the same example I use when I teach set theory in the cybersecurity context. Why do we teach traffic lights in the cybersecurity context? Traffic lights can do something unsafe, which is that they can have a yellow to green transition, or they can have a green to red transition. Why is that? I'm driving, I'm looking at a green light, I perceive that I don't have to slow down because there's no yellow. The light atomically transitions to red, I can't stop in time, I collide with an 18-wheeler full of dynamite, and I have a very, very exciting, very short remainder of my life, right? So that is the unsafe condition. So what this means is that green, yellow, red, it is possible mechanically for a light to transition between any of these edges, right? It is unsafe for it to transition between some of them. But we can illustrate the Cartesian product by looking at all of the products together. We have 3 colors. The colors can transition somewhere, so that means that each color can transition to 2 other colors. I believe that's 3 choose 2. Anyone do combinatorics? I'm pretty sure this is 3 choose 2. Ask probably Professor Otto. And so there are 6 possible options here, and I think of them as being 2 pairs for each of the 3 colors. So green can go to yellow or red, yellow can go to red or green, red can go to green or yellow. Order matters. So a relation R over a set S is a set of pairs of elements of S. And we can define the traffic light as a subset of the Cartesian product. So the Cartesian product of colors is colors cross colors, and we're going to look at a subset of that set when that set is created with an operation over 2 sets. Okay? So I'm squaring the set, and I'm going to take part of it. You looked a little more confused on that slide than on some previous ones. That's okay. I have absolute confidence in you all. It's going to make sense here in just a sec. Okay. So we're going to construct L, the traffic light relation. I think the most important thing, and I gave the example of the atomic transition from green to red. That's bad. So I think what we want is no red without prior yellow, which means that for all of the pairs in L, if we have yellow first and some value second, it must be the case that the second value is equal to red. Okay? And then we also have all colors must appear in both positions, so we must be able to continue to have a progress mechanism. Something I think is very unsafe, this isn't an urban planning class, right? But I think if a traffic light stays red for like 5 minutes, basically no human can resist the urge to drive through it while it's red. So it is like deeply unsafe to not cycle your lights fast enough. And it's like even over 3 minutes it starts getting sketchy. Personally, I just run every red light, so I don't know how long other people wait. Don't put in the course of vowels. I think that might be a felony. Okay. Personally, I ride my bike everywhere, and so I don't look at red lights. I only look at the white person and the red hand. Okay, so all colors must appear in both positions. That just means we have progress mechanism and no one's going to run red lights. Okay, so what this means to me, I think, is if I apply those constraints, then I get the following relation: green to yellow, yellow to red, red to green. We don't knot this. We note this is a subset of the Cartesian product. Okay. There's a lot of ways to express relations. And one obvious reason for this that you can imagine is that we have different ways to express things in like most programming languages. So I can say 1 plus 1 and use infix notation, right? I can say add 1, 1, to use prefix notation, and as a rule, people don't get too confused by this. Let me show you the worst thing that I've ever done in my life. That's slight exaggeration. So I was hanging out. I was hanging out in CS 151, and I got to teach classes and methods last week. And I don't like classes and methods very much. So I show students some of the like crazy things going on under the hood, so they have some appreciation for why someone might not be opinionated about them. And so I showed them this example. So you can do 1 plus 1. And you can also do parenthesis 1 dot double underscore add double underscore parenthesis 1. And that's the same thing. One of these is easier to see and explain and understand, right? The same thing is going on with set relation notation, but there's one other thing that's really important about this. This is probably an easier way to show addition, but this is absolutely not an easier way to represent how addition is implemented in Python, right? This is the correct way to show this because addition is a method in Python, right? So I would argue this is like more correct in that it's showing you you're not adding two numbers together, but you're performing an add method over two instances of the integer class, right? Which is a different thing and is more true to form. So depending on what you're trying to emphasize, you might want to think of this as a function, such as the light of green is yellow, or you might want to say, oh, this is just a relation that I'm describing, which is that green, light, yellow is something that happens, okay? So you can express these in different ways. This is an adjacency matrix, which is another way to explain it, which is that green is adjacent to yellow, yellow is adjacent to red, and red is adjacent to green. By the way, this is extremely information dense. You only need 9 bits to store this, right? You have to know the order, but... And of course, how many bits does it take to store 9 bits? Well, you have to use 16 because you have to go up to the next 8. So like, I don't know. I'm doing what I can here, right? We can also look at the rainbow relation, which is a very fun relation. Are any of you in computer vision this term? I think in the computer vision class, like wavelength comes up all the time because you're always sorting colors and you have to put colors in order and you might not always be thinking of them as RGB. Oh, there was a physics call out on that slide. I think I went fast enough. I think I'm safe. Here's an example of a different relationship over green, yellow, red. So over green, yellow, red, we can sort them by the traffic light relation, but we can also sort them by the wavelength relation. And what is the wavelength relation? Well, red is higher than yellow, which is higher than green. So we say red is higher than yellow, or yellow is lower than red, whatever you want to say, right? It's a directional relation. We say green is lower than yellow, or yellow is higher than green. And we say green is perhaps higher than nothing, so there's nothing in this column at all, which we express with set nothing. I believe that is that var nothing? Yes, so that's var nothing LaTeX and whatever you want in HTML. So we're going to take the rainbow relation B. Why is it B? Because R is taken for relation, so I'm calling this relation B. It is also a binary relation. It is a subset of the Cartesian project of GYR, right? And it has only these relations, red to yellow and yellow to green, and that's above. So we also note that red is above green. I am leaving this out. Why am I leaving out the red above green? Because that is not an atomic relation. There's an intermediate yellow. I really have to figure out who is messing with my slides. Is this annoying you all? Or do you like, is it cringe? It's a little, yeah, okay. Do you know how annoying it is going to be to write the regular expression that fixes that problem? It's going to take me like minutes, and then it's not going to work the first time. Okay. Regular expressions are edges between the set of possible text files. So that's crazy, right? But it's true. I mean, that's what they are. Regular expressions are edges. Okay. So transitivity is over relation R as follows. Sorry, putting a pin in this. I've shown you two relations. Now I'm going to show you transitivity over them. Okay. I've stressed the importance of atomic edges. Transitivity does not care about atomic. The transitive closure is if there is some series of edges that connect two things, I regard them as connected. So, if A to B is in R and B to C is in R, then A to C is in R. That means the relationship R is transitive. I have thus far shown you no transitive relations, okay? For us, that would be red is above yellow is part of the rainbow. Yellow is above green is part of the rainbow. And that would mean that if we had the transitive rainbow relation, not the atomic rainbow relation, red above green would be part of the rainbow. So, this relation is not transitive, but we can make it transitive. So, how are we going to do this? We're going to perform an operation called the transitive closure. What is transitive closure? It is essentially a function that accepts a relation. A relation is a set of pairs, and it's going to produce a new relation, which is also a set of pairs. How is it going to do this? It is going to add additional pairs to the set of pairs until this statement is satisfied. So, a closure is an operation over sets. We're going to denote the transitive relation, or the transitive closure of some relation, which is not necessarily transitive, R as R plus. That's R raised to the power plus. This is LaTeX. That was the only way I could describe it. No graceful way to do this in HTML, but you can use superset elements. Okay. So the transitive closure R plus of some relation R must contain all elements of R. So it has to have all of the pairs, all of the connections that are in R. And we're going to use set operations to do this. So we're going to use set operations like superset. And basically, R plus, the transitive closure, is going to be a subset of this thing, which is all of the possible pairs. Okay? So, for all pairs of colors in the binary relation R, each one of them is also in the transitive closure of R, R plus. So, for all pairs in R, the pair is an element of the transitive closure. For all xy that are elements of the underlying set, such as the set of colors or the set of stations, that pair xy is part of the relation, which is a subset of the Cartesian product. All of these have to be in the transitive closure. So the transitive closure has at least as many pairs in it as any given relation. And then we have the additional requirement that, well, what's so special about this thing if it just has all the same elements in it? Well, it also has to satisfy the transitive property, so it must satisfy transitivity. So we're going to add sets. Add an element until you get transitivity. Previously, I mentioned there's not necessarily always a gracious way to show that things are connected. Here's what I tried. I just italicized it. This is what the way I read that is Seattle Amtrak Tacoma. The Seattle Tacoma is a member of the Amtrak relation. I don't know, right? Like, am I supposed to put plus there? I don't know. Should I say Amtrak of Seattle Tacoma equals true? I don't know, right? So I just wrote Seattle Amtrak Tacoma. And why do we have Seattle Amtrak Tacoma? Because we have Seattle Amtrak Tukwila, and we have Tukwila Amtrak Tacoma. So they are connected. And then we also have Seattle Amtrak Olympia, which means we now have Seattle Amtrak Portland. Congratulations, we have now connected the great city of the Pacific Northwest and also Portland using Amtrak, right? Oh, why did I not use color before? That looks so much easier. Like, I should have always been doing this. That red looks great. That really popped for me. It even looks good on the projector. It actually looks way better on the projector than my screen. Don't those colors look nice? Okay. Now I feel like wildly inadequate. I don't always have those colors. Okay, so if in rainbow relation B, we find R is higher on the rainbow than Y, and Y is higher on the rainbow than G, Then we have ry, yg. The transitive closure just adds rg. Easy. And then what is the last requirement? This requirement matters a lot, and it seems a little deceptive. The transitive closure must be the smallest possible relation that satisfies the transitive property. Why is this? Well, otherwise you just take the Cartesian product, because the Cartesian product already satisfies transitivity because it has every collection of every pair, so it's not missing anything. But you probably don't just want everything, or you'd have taken the Cartesian product, right? So the transitive closure of a relation is the smallest closure satisfying transitivity. So those binary relations are graph edges between graph nodes, and all those edges, those are the pointers. Those are your boxes, or the reference backwards. So what we're talking about here, it's like math, but it's also like how objects are created in program memory and how they are stitched together, right? So we're going to keep going. Okay. I'm not going to finish this today, am I? Man, the planned lab for Wednesday is cool, too. I think I was just going to make you make a binary search tree, which is like not hard in Python, and then you do it in Rust, and you're like, oh! Or that was the noise I made when I did it. Has someone made you all make a binary search tree yet? Did you also make a balanced version? AVL or red-black or something? Okay. Fewer people are nodding each time I ask, but some people are still nodding, which is curious. What class did you do it in?
Algorithms.
Oh, in algorithms. Okay, so some of you have taken algorithms, some of you only taken data structures. Okay, that explains everything. Okay. What, did you do algorithms in Python? Okay, cool. I like red-black trees a lot, so I might have you do those, but I don't like implementing them. And should I make you do something I don't like doing? Okay. We're going to use transitive closure to define cycles. Why are we defining cycles? You thought I got lost in the weeds. This whole time we've been setting up to define directed acyclic graphs, right? You thought I forgot. I didn't forget. I knew what I was doing. We're going to consider the graph G, V of E, and we're going to note that E is a homogeneous binary relation over V. So the edges are a homogeneous binary relation over the vertices. If we take the transitive closure of E, of the edges, then what are we going to say? We are going to say G contains a cycle, which is logically equivalent to having the property of being cyclic, or cyclic, if the transitive closure of E contains an edge from a node to itself. It can be an edge from any node to itself. All we need is we need one of them. So cyclic of the graph is equivalent to there exists some vertex in the set of vertices such that there is a vertex-to-vertex edge in the transitive closure over E. This, to me, is like what makes doing the set theory worth it. That you can just rigorously and completely define what it means to be a cyclic graph. And just, like, this is that 12 characters of LaTeX or something? Like, it's so simple. And it's, otherwise you're doing all these things where you're like, oh, there's like a way you can create a loop and all that stuff. No, it's just a transitive closure. That's all it is. Okay. By convention, cycles are defined to be non-trivial, which means you assume that the graph didn't start with any edges from a node to itself. So this is, can I take Amtrak from Portland to Portland without going to any other stop? No, I guess, right? Like, you can walk into the station and walk back out. Is that really taking Amtrak? So when we say non-trivial, it's like, usually what we're doing is we're pushing up against what we're abstracting with the notion of graph theory, and it's like, is it meaningful to say you can do that? So in this case, we say there is not an edge from Portland to Portland. But I could put one there. I could get on the bus and like drive around the block, right? But like by convention, we don't do that. Okay. There exist other terms, and I'm going to tell you what these terms are because you might see them on Stack Overflow, which again, it seems like we don't have to go to as often. I think we don't go to Stack Overflow as often because Wikipedia is getting better. I think that's where I go instead. And then in this class, rustc is good. So I like keep having to not look up things because rustc tells me what to do. And I don't think rustc is going to tell me I can't. No, it did. I wrote a circular struct definition, and it told me that formed either a cycle or a circuit or something. So there was. Hold on. This is worth checking. It was right here, right? No, it's in box. Okay. Cycle. Boom. Valid. Okay. See? Did you know what cycle meant? Yes, you did, but now you know more. Okay. Circuits, walks, paths, and trails are also defined in graph theory. The other way I would have taught this other than transitive closure is with paths. Direct paths and undirected paths are not the same thing. But there is, I don't know. They're useful when you don't want to take the whole transitive closure, basically. Okay. So this is a DAG. A DAG is a graph G equals VE that is a directed acyclic graph. In order to do that, it has to have edges that are directed. So E has to be a set of ordered pairs. And the transitive closure of its edges, E plus, contains no identity pairs, so no self edges. Okay. Cascades 503, which starts in Seattle and ends in Portland, is a directed acyclic graph. I cannot take the Cascades 503 from Seattle to Seattle. I cannot take it from Portland to Portland. And I can only take it in one direction. Amtrak Cascades is not a DAG because it is not directed and it contains cycles. I can take Amtrak Cascades either direction from Portland, and I can also take it from Portland to Portland. Color wavelength is a directed acyclic graph. Red is above yellow on the rainbow, and it is above green on the rainbow, and yellow is above green on the rainbow. So this is an example of a DAG. Traffic light is it is a directed graph. I don't know why that says not, but it is cyclic because it goes green, yellow, red, so there is a cycle. One of my favorite Ridley Scott films, Thelma and Louise, doesn't represent a directed graph because Thelma is friends with Louise and Louise is friends with Thelma. Friends is a symmetric relation that is not directed, so that is not a DAG. And for that reason, I think Facebook is not a DAG. Can you be friends with someone who's not friends with you on Facebook? Does anyone still do Facebook? Yeah, so Facebook's not a DAG. But I think Instagram is because you can follow people that don't follow you, right? And so that's why we have mutes or whatever, mutuals. I don't know how that works. The Bachelor's of Science in Computer Science is a directed acyclic graph because there are prerequisite relations, basically, that are directed. You would probably be surprised how often you see a curriculum proposal that involves a cycle, where a class is a prerequisite for something that is its own prerequisite. That happens from time to time. And usually that's when two different people teach different classes and they both want to be second. So like, for example, you may have noticed that there's like a little bit of mathematics going on in this class. I'm trying to get CS 271 after Math 251, right? But no one wants to let me do that because then I will become too powerful. So those are DAGs. Okay. And now when someone says dag nabbit, you know what they're referring to. All right, sorry. I can stop. Okay. I'm definitely having more fun than all of you, and that's completely fine with me. Okay. Trees are easy. A tree is a DAG where every node has at most one incoming edge. So, we had, can you all see this? Okay. Red was above yellow, was above green. This is a DAG but not a tree. It is not a tree because green has 2 incoming edges. How do we make this a tree? If you switch to atomic, then it becomes a tree. Trees are pretty useful because you can go backwards through them. Not always super easy. There is apparently such thing as undirected trees. I didn't actually know that. I looked up the formal definition of tree, and I was pretty sure it was going to say DAG where you have at most 1 incoming edge, and that is completely fake. There is like a massively complicated definition of tree, and I was running out of time to do more formalism, so I'm actually just not going to teach you what trees is. I'm going to say it's a DAG with at most 1 incoming edge, and we're just sorry. I taught you what ordered pairs are. That's all I can do, right? A graph G equals V is a tree if for all the element of the set of vertices, the cardinality of the set of incoming edges, so this is all pairs where the second element is the vertex, we cap that at the size of 1. Not everyone has to have an incoming edge, but you can't have 2 incoming edges. So for all vertices, the cardinality of the set of incoming edges is less than or equal to 1. Okay. One example of these is a decision tree. I'm running out of whiteboard space. So I walk into my favorite copy shop 5 days a week. Why is that? Because this class goes until 2:40. It takes me 10 or 15 minutes to walk to my car, 40 minutes to drive home, and then it is a 20-minute walk to my favorite coffee shop, which closes at 4. So that means I don't go on Mondays and Wednesdays, but I go every other day of the week. But I would rather spend my time with you, so that's no burden to me at all, right? When I walk into my favorite coffee shop, I immediately am faced with a decision tree. I have to decide if I want a hot or cold drink, if I want a small, medium, or large drink, if I want for here to go. This is a tree, and the leaves at the end of the tree are the tasty drinks that I can take home with me. But I don't, of course, because it's a zero-waste coffee shop, so they don't give you a to-go cup, so you usually finish it there. And I would have to carry my own cup the 20-minute walk to it, so I always just do for here. So that is an example of a decision tree. This is a decision tree related to spending money, I think. I found this from, like, management theory. You may know that the dean of our program is Jamison Watts, who got a business PhD, and he's always trying to get me to study decision theory. So I put this in here in case he walked by class today. Let me check. Oh, the light's on. Okay, so when this class is over, there's an office right there. Just stand outside of it and say, like, management science decision systems, like, loudly a bunch, okay? Just do that for me, okay? You can do that whether you're my friend or my enemy, because I don't know what'll happen to me when that happens. Okay. My favorite one, this one's naturally occurring, river systems. It is virtually unheard of for a river flowing downstream to split into 2 channels for any non-trivial amount of time. So this is really cool. So for example, the Willamette feeds into the Columbia. There's only 1 incoming edge from the Willamette into a larger river. So if you flip that backwards, right, the Willamette only comes out of the Columbia once when you're going inland, which means it's a tree. So I was really proud of this one. I hadn't actually seen anyone else come up with this, but I wanted a naturalistic example, and river systems are trees. And then there's also these little things called data structures. Anyone heard of data structures? We all love data structures. Okay, I don't like them either. Okay, that's fine. Why trees? If you're trying to store data, you really only need 1 unique path to the data, and oftentimes it is better to only have 1 unique path. And if you're trying to assure the integrity of data with hashing, you really only need to hash once. So if you are using SHA 512 or 256 over some file system, or over changes to a file system, perhaps in a version control system, you're going to want to do that uniquely. So you're going to want to enforce the tree property over whatever your data representation is. Okay, so this is a sample tree struct. This is, what language is that? Oh, that's C. But we can do this just as easily in any other language, right? Probably you did something like this in another class. Is this how you write Python? Or maybe it has like a left and a right. This is how you would do a tree in Python, right? And then, of course, you don't actually have to do trees that way. Separately, you can also do, and what are you going to do? You're going to do self, and then you're going to do vertices, and you're going to do edges. And you can use either alternative formulation. The only difference is, in this case, you have to verify the acyclic and the tree property over V and E. So you have to do if not cyclic E, basically. So a variety of ways to explain this. My favorite tree is, of course, the binary search tree, where you sort integers. My favorite combination of integers to put in, I'm going to write this down because you might need to test it later. 5, 3, 7, 2, 4, 6, 8. If you put in your numbers in this order, it will always come out balanced, which is really nice. And so commonly when we are using binary search trees, we will use this to construct. Okay, I want to make it. We take 5, we place it in the tree. You know this already, this is just review. You take 3, you put it in the tree, you check to see if it's larger or smaller than 5. It's smaller, so it goes to the left. 7 is larger, so it goes to the right. These are directed edges, because they're lower in the tree. Then we place 2, 4, 6, and 8. This was my first exposure to a tree, was the sort of binary tree struct. And importantly, is that how it works? If you declare one of these in Rust, I guess we'll use these. If you have a left, which is going to be a tree T. I'm not going to put the, well, we'll put the right in. Can I run this? We are not allowed to just naively put elements of the tree back inside the original trees, because that would cause there to be a cycle, and then our code explodes. So you somehow have to solve this problem of we can't put trees directly in other trees, right? And this is the transitive closure problem. Okay. Something you have probably realized is that if you already had access to a tree, it would have been very easy to implement a stack or a heap. Why is that? Let's see. You just don't use this. You just only use one of the branches of a tree. A singleton linked data structure is already a tree. It is just the very boring version of a tree, where you only have a single outgoing and incoming edge. So just don't do that, but you can if you want to. Why does this matter? To me, when I first learned about the BST, it was non-obvious that this wasn't sort of like a golden ticket to really good complexity, right? My line of thinking was, oh, if I put any series of numbers into a binary search tree, the depth of that tree is going to be the log of the length of numbers, and I'm going to have an n log n sorting algorithm. That's not true, because in the worst case, a tree is in fact identical to a linked list in terms of depth, which means that your worst case time complexity for everything involving trees is exactly as bad as your worst case time complexity for anything using lists. That just happens to occur at low probability. So look out for this. I think you know this. And then hopefully you're aware of the symmetry between quicksort and binary search trees, where when I inserted these values here, so quicksort would also be very fast on this list, the choice of the pivot point is extremely important to the eventual performance of my sorting algorithm. But if I started my pivoting on 2, then this would have n squared time complexity. Where we're going with this is it is not my eventual plan for you to be like super good at writing binary search trees in Rust. There is already B-tree map. I have used binary trees in map in Rust. I had to use this in my research for something. It seemed to work great. Like I'm not going to ask you to implement this, but also like I've sort of now shown you like some of the typing stuff. So like there's a lot of nonsense on this public struct, right? Like we have different, and so this is the key type, the value type. I don't remember what the A type is, but that's not what I am necessarily interested in you doing this term. The application of trees this term is going to, I hope, be much more interesting, which is that I'm going to teach you about Merkle trees or hash trees next week. The Merkle tree and the hash tree is also very similar to the stack allocated version of a heap, and a heap is itself also a form of tree. So, what is interesting about these things? They are not sorted. They have no notion of sort of ordering. They are ordered arbitrarily by like when you place things in them. What does this mean? This means we can always keep them balanced with no consideration of the cost of something like a red, black, or an AVL tree. So they're guaranteed balance because we just always put something in the last position. And they are very useful because you can hash up from the bottom to the top or the top to the bottom, sort of however you perceive it. And then you can make assurances about the integrity of all of the information placed inside the tree. I learned about Merkle trees from blockchain, and so they were involved in the blockchain class last term. I did not know they were used in Git. I found out they were in Git. I looked up, does like anyone else use Merkle trees? Yes, it's super foundational Git. So far more Merkle trees are used in version control than are used in blockchain, which is good because version control is awesome and blockchain is terrible. So they're still independently useful this term. And it is a super, super high performance version of the tree because it's inherently balanced. So this is what a Merkle tree is going to look like. Oh, are we out of time? Sorry. Oh, I was off by 2 minutes. Okay. See you on Wednesday for lab, Monday for Merkle tree. Everyone okay on traits? I didn't think traits was that bad, right?